Welcome back to ECE 442-542. This is lecture 5.4, and in this lecture we have a couple of goals. One is, where did this formula or expression to create the controller come from? Let's now derive that so that you have an understanding of where we're coming up with this particular expression or formula. And then we'll try to provide a little bit more background on why do we have these restrictions in our Ragazzini design controller approach. Let's start by deriving this design formula, which is 1 over g of z times t sub c of z over 1 minus t sub c of z. And c of z is our controller. Hopefully we are remembering all of these different transfer functions. C of z is our controller's transfer function. G of z is our plant. And t sub c, which appears two different places, one in the numerator and one in the denominator, this is our desired closed loop transfer function. The goal really for this controller is to find this transfer function, capital C of z, such that when you put that into the closed loop unity output feedback configuration, that you actually obtain between the reference input and the output this closed loop transfer function t sub c of z. If you build your controller based on this formula, then your closed loop transfer function between the reference input r and the output y will in fact be t sub c of z. So now let's find why that is true. Why do we have this expression or this formula as a result of wanting the controller C of z to actually accomplish, when it's in this closed loop configuration, it actually achieves the closed loop behavior that you want between the reference input r and the output y. Here is our assumed configuration for the closed loop system. We have the plant and we have the controller. Those are both in the forward path, and we only have unity output feedback, or y is coming back without being filtered and being compared with our reference input r of z. We want now, in fact, for this closed loop transfer function, that's now assuming, maybe if I can erase that, that's now we want this transfer function. I don't know that I like that one path, but now this big block between the reference input r and the output y, we want this controller to be such that what's in the blue highlight is what we want our closed loop transfer function to equal. We want that to be our closed loop transfer function, t sub c of z. That's what we desire. Let's now derive the relationship, or let's just remind ourselves of the transfer function expression between r and y in terms of the plant transfer function g and the controller transfer function c. In this case, we can hopefully see that y of z is g of z, c of z times e of z. We can also define e of z. E of z is the error signal. That's the comparison of our reference input r with the output that we see coming out of this closed loop system. That's E. This is now y in terms of e. Let's now use that e to eliminate e and express or try to find an equation or a formula that only contains the output transform y and the reference input transform r, and then we will be able to find the transfer function that we want. Now we can say, or we can express, y of z is now, and now I'm going to go ahead and just not be keeping track of these arguments on g, c, y, well, and r. So now we have gc times e, but e is just r minus y. Again, this is e. We're just substituting that where we said it needs to be. This now says that y of z, I'm not sure why I'm keeping that y of z, so let me not keep that y of z. Let me now combine the terms involving y and the terms involving r. I have this coefficient of y, and then I have that coefficient for y. If I add gcy to both sides, I now have that on my left-hand side. The gc minus gcy on the right-hand side has now been canceled by adding gcy, and I'm left on the right-hand side with gcr. If I simply now divide by the transform expression that's scaling y of z, I now obtain my closed loop transfer function expression in that unity output feedback configuration between the reference input r and the output y. This is now we want this to actually equal our desired closed loop transfer function. So if we now have t sub c being equal to gc over 1 plus gc, now can we solve this for c, and that will then force the closed loop system to have a transfer function between the reference input r and the output y in the closed loop to equal t sub c of z by the appropriate design of our controller c of z. Let's now use this t sub c expression to solve for the controller's transfer function c of z. Well, now let's just cross multiply or multiply both sides by 1 plus gc. And now we can distribute that t sub c through the two terms on the right. So we now have t sub c plus gc t sub c equaling gc. Again, we're trying to solve for c in this formula. Let's now put some c terms on a side by themselves, or we can now subtract gc t sub c from both sides. And because we're dealing with scalar transfer functions, we can really interchange the order of these transfer functions. So now I've simply, this was what we were calling c t sub c, but since these are scalars, they commute. So we're now writing that as t sub c c, and we can now factor out a g on the left, and let's factor out a c on the right. So that means we're going to have a 1 in the first term on the right hand side, and on this second term we have t sub c. This now allows us to divide both sides by 1 minus t sub c and divide by g, or simply solve for c. C is now t sub c divided by g of z times 1 minus t sub c of z, and that is the direct controller design formula that we were after at the beginning. We were trying to derive this. If we now create c of z, our controller transfer function, based on this relationship, we will now know by construction that the closed loop transfer function between the reference input and the output will equal t sub c of z. What do these, or now that we have this design formula, where do these Ragazzini restrictions come from? And first, looking at this design formula, if you didn't have that second expression on the right, you would see that you have now c is 1 over g. And what is that saying? Well, that's basically saying you're trying to cancel the plant's dynamics with the help or by the choice of the controller. But if this was all that there were to the design, then if you had unstable zeros in G, the C, the controller, would actually be trying to cancel those, because now in the forward path you have G times, or C times G. And here we're saying, oh, if we just had 1 over G, then now whatever was unstable here is going to be canceled by what's now in the denominator of our controller, and these, the polynomial here in the denominator of G is now going to be up here as a 0, and that's going to cancel the unstable pole factors in our original plant. And we do not want that. We know from our discussion before, to have an internally stable system, we actually need no unstable pole zero cancellations between our plant and controller. So the first, or the two middle restrictions, restriction 2 and restriction 3, are trying to avoid having our controller C of z in fact perform those pole zero cancellations. And the way that we're doing that is we're actually forcing those unstable factors, zero factors in G of z, to not be existing in our controller C of z. And we are also trying to eliminate those unstable pole factors in G of z, becoming unstable zero factors in C of z, and we're doing that by the choice of t sub c of z. And that t sub c of z appears in two different places. It appears in the numerator of this bracketed expression on the right, and it also appears in the denominator. So now what we're going to do, I should have this actually being a little bit bigger. So 1 minus t sub c of z, that's proper. If you look at what that is, you can see that if you now rationalized the denominator, or I'm sorry, obtained a common denominator between 1 and t sub c of z, you would put both of those over the same denominator, and now what's going to happen? Well, now 1 is the denominator over the denominator. So whatever the degree of the denominator was, that's now the degree of the numerator of 1 minus t sub c of z, since you have denominator minus numerator in the numerator expression of 1 minus t sub c of z. We want this particular expression, this 1 minus t sub c of z, we want that to have a 0 in the locations that actually are associated with unstable pole factors in our original plant g of z. So this lower circled location in capital G of z is representing the unstable pole factors in our plant, and we want those to be canceled by 1 minus t sub c of z so that they do not show up in our subsequent build of our controller c of z. So we're canceling those in the design step so that c of z will not have those factors present in it. And if they're not there, then it can't, when you put it into the closed loop transfer function, you can't then cancel those unstable closed loop poles in the plant G of z because they have now been removed from your controller C of z. Likewise, restriction 2 says if you have unstable zero factors in your plant, which is now what is right there, that's the numerator of G of z, what you want to do is retain those factors, unstable zero factors in T sub c of z. Now T sub c of z will cancel those factors in G of z, and that will keep them from appearing in C of z so that they no longer will be canceled by poles of your controller C of z. That's now really the middle two restrictions, the explanation of those. That's why we have to have unstable zero factors from our plant remain in our desired closed loop transfer function T sub c of z. That's restriction 2. And that's also why restriction 3 is concerned with keeping our unstable pole factors in the plant out of our controller C of z, and we do that by canceling them in the design process or in the build of our controller C of z by forcing 1 minus t sub c of z to be a 0 when z is equal to the unstable poles in G of z. If G of z does not possess any unstable zeros or any unstable poles, restrictions 2 and restrictions 3 are not needed. So we wouldn't have to worry about restriction 2 and restriction 3, and we would then have more freedom in the design of our closed loop transfer function capital T sub c of z. Those are the middle two restrictions. What about restriction number 1, the first one, which was concerned with the pole zero excess in your plant matching or at least being less than the pole zero excess in your desired closed loop transfer function T sub c of z. So we want the pole zero excess in G of z in our original plant. That, remember what C of z is doing. C of z had in it really this inversion of G. And if we had a pole zero excess of 2 in G of z, then those two poles will actually flip up and become in the numerator of your controller, and now your numerator polynomial is of higher order than your denominator polynomial in the controller, and that will give you poles at infinity. So we talked about zeros at infinity, and somebody asked, what about negative zeros at infinity? Well, really, those are referred to as poles at infinity. So the pole zero excess in our original plant will result in poles at infinity in C of z, and we don't want that because that will cause a non-causal control action unless T sub c of z possesses at least the same pole zero excess at G of Z. So if we can make sure that T sub C of Z has at least the same pole zero excess as the original plant G of Z, then we will not have this non-causal behavior in our controller. Because poles at infinity in our controller produce a non-causal characteristic. Where does that come from? Well, let's now go back to our block diagram. Here is the input to the controller. That's our air signal. And here is the output of that controller. So in terms of a transfer function, we have the output U being C times the input E. That's what we're starting with down here, just to get a feel for what's happening. So U, the output of your controller, is C times E. What happens if we would actually have a pole at infinity? Well, a pole at infinity could be obtained if we simply had U of Z equaling Z times E of Z. Here would be our controller that would be, what would its pole zero excess be? It wouldn't have a pole zero excess. If C of Z is equal to Z, then we have a pole at infinity. Because if C of Z is equal to Z, as Z goes to infinity, what happens to C, that transfer function? It goes unbounded. That's the definition of a pole. So that's now a pole at infinity. This is the simplest way of producing or realizing a pole at infinity, to just have a transfer function equaling Z. There the numerator order is 1, the denominator order is 0. You have a improper transfer function. But what does this look like now in the time domain? That's the frequency domain relationship, U of n, and what does the Z operator do? That's an advance in time. That now basically says, or would require, that the present input to the plant needs to actually be equal to a future air signal. So somehow we're able to tell the future in a non-causal controller, and that's not going to happen. So we have to make sure and not request the impossible, and that's where restriction 1 is coming from. So this restriction on the pole zero excess in capital T sub C of Z makes sense. Suppose the plant had a pole zero excess of 1. Then G of Z would have 1 sample period delay between the input and the output if it has a pole zero excess of 1. And a simple case now is G of Z is 1 over Z. The pole zero excess is 1. We have 1 pole, no zeros. The pole zero excess is 1. That's Z to the minus 1. That means then that Y of Z for just this system is GU, but in the time domain that says now that Y of n is equal to U of n minus 1. So we have a 1 sample period delay between the input U and the output Y. The Y at the present time is equal to the input 1 sample period earlier. By forcing our desired closed loop transfer function T sub C of Z to have a pole zero excess of 1 means we are forcing that desired closed loop transfer function to have at least the same amount of delay as the original plant. We can't remove delay with our controller. Doing that actually would say that we can predict the future, and we can't. So T sub C of Z, restriction 1 says T sub C of Z, the desired closed loop transfer function, has to possess the same or more pole zero excess as the original plant G of Z. So we've talked about restriction 1, restriction 2 and restriction 3. Restriction 4 was dealing with steady state accuracy. Or what does that mean? Well, steady state accuracy now puts some additional constraints on T sub c of z. Up until this point, restriction 1 said put restrictions on the pole zero excess. Restrictions 2 and 3 put restrictions on the zero factors in T sub c of z, and it also put restrictions on the zeros of 1 minus T sub c of z. Now we're putting more restrictions on T sub c of z through restriction 4 when we're talking about steady state accuracy. Here's an example, or here are ways of thinking about this fourth restriction. The error signal is again the comparison between the reference input R and the output Y, or R minus Y. And Y is just the desired closed loop transfer function T sub C times R. So R minus T sub C R is E. E now is simply factoring out the common R of Z in both terms on the right. E is now equal to 1 minus T sub C of Z times R of Z. And what does that relationship tell us relative to the error? So let's look at that for the two different cases that we will focus on in this class. Suppose now the reference input, constant reference input case, so now R of Z is a constant. What if we want zero error in our system? So we want E to actually go to 0 in the limit when we have a constant reference input. To have a constant reference input in the frequency domain, that's AZ over Z minus 1 for R. And from the final value theorem, we know that the error, we want the error to go to 0 as the time index n moves to infinity. Based on the final value theorem, that's equal to the limit as z goes to 1 of z minus 1 e of z. But e of z is 1 minus t sub c of z r of z. So that now we plug that in and we now see that we have the limit as z goes to 1 of this factor z minus 1 times the error signal, which was 1 minus t sub c r. Here is r, and this is now e of z, 1 minus t sub c r. But you can see that r possesses a pole factor equaling z minus 1. That now cancels the z minus 1 factor in front. A is just a constant. That's not going to influence what happens as z goes to 1. As z goes to 1, that's not going to influence anything. So in fact, what we are trying to do is we're forcing the bracketed expression to equal 0 as z goes to 1. In order to do what? In order to make sure that our error, e, in the limit goes to 0. So we want 0 error due to constant inputs. That now tells us that we want 1 minus t sub c of z as z goes to 1 to equal 0. Well, that's the same as saying the limit of t sub c of z as z goes to 1, that equals 1. And that now gives us a DC gain constraint on our closed loop transfer function. We want this closed loop transfer function t sub c of z to equal 1, or we want it to have a DC gain equaling 1 in order to have 0 error due to a constant reference input. Now if somebody says, oh, actually I need you to have a certain behavior due to a ramp input, That's now making things a little bit more challenging than a constant input. Now our input, reference input, is a ramp. Well, now you need to look at both the ramp condition and the constant condition. So the first step is really to satisfy the velocity error restriction or constraint. And if you work through the analysis, you'll end up with 0 over 0. So you'll have to invoke L'Hopital's rule. And that now says that minus t, where t is the sample period, times the derivative of the desired closed-loop transfer function with respect to z, that needs to equal 1 over k sub v. So here you're wanting your error due to your ramp input in the steady state. You want that error to be 1 over k sub v. You now have that specification, 1 over k sub v. You use that. T is known, so now you use the freedom or the flexible parameters in t sub c of z. You'll have to maybe introduce some more parameters in your desired closed-loop transfer function to allow you to achieve not only this relationship, but you also need to ensure that the original relationship on your constant input is still valid, which is t sub c of z when z equal to 1 is equal to 1, or you have a DC gain of 1. So the first step is to satisfy the velocity error constraint if you have one, and the next step is really focused on this constant input condition. You now want to achieve a constant input error constraint. Which is really just restating what was the win up above, but I'm just trying to emphasize that you probably will want to do them in this order. First, address the velocity error constraint, and then use the leftover available parameters in t sub c of z to achieve this DC gain of 1 in your desired closed-loop transfer function. That now is explaining this Ragazzini controller formula and the restrictions.